So I think we should get started. I think we're probably officially out of seats. Thank you all for coming. I'd like to introduce myself. My name is Andy Wilson. I am a principal researcher at Microsoft Research. I also manage a group that we call ourselves Natural Interaction Research. We do a wide variety of research in a lot of different kinds of topics, everything from social computing to the things I'm going to show you here, to learning different models of attention while driving, for example, is a topic that we're looking at. So we do a lot of different things, and what I'm going to show you today is mostly about my research, and along with a few collaborators. And what I'm going to try to do is give you a sense of the things, the prototypes that we build, and I'm going to overwhelm you with video. All of the stuff that I work on is very visual in nature, and so I'm going to show you some video. I'm not going to get too technical or too into the details, and I'm happy to chat with you afterwards about all of this kind of stuff. I understand everybody here is probably a developer, which is great. While you're watching these kinds of things, maybe think of some questions about how some of this stuff was put together, and I'd be happy to answer that. Everything you'll see here is, these are research prototypes. These are not necessarily meant for productization or any sort of production environment. Some of these things hang out in our lab over in Building 99 and run for a year or two, and then we take them down and we build a new thing. So they're mostly one-offs. Some things I've been lucky to work on some projects that have been productized. So I've worked on inertial pointing devices. I've worked on the early version of Surface, not the Surface that was launched recently, but the large tabletop, the 30-inch tabletop. And I'll show you some really early version of that, which you might find interesting. And then I've also worked on the Kinect and worked on some of the very earliest depth camera prototypes. And I'll show you some of the things that we did there. So supernatural interaction, right? So that's kind of an intriguing title. It is Halloween, right? We're not talking about ghosts and goblins and that sort of thing. But what I'd like to suggest to you is to think about what makes natural interaction. Why is natural something that we're so focused on these days? And in particular, why would you want a natural interface? Why stop at natural? Let's talk supernatural. You don't want to merely emulate the real world. We have a very nice real world. If you want to emulate playing with blocks on a tabletop, maybe the best thing to do is actually get blocks. So you want to manipulate millions of blocks. You want to be able to have magical powers over those blocks. You want to be able to do it over the network from many, many miles away. You want to be able to have the exact block that you want. These are the things you might want in a supernatural interface. So that's just a little bit of an entree. What I'm going to do is run through a bunch of videos of projects that we've done, but I'd like you to think about the three following themes. First is this concept I call analog interactions. And I think one of the things that I find very amazing about the evolution of digital computing is that as our machines become bigger, faster, more storage, more power, more graphics, they become less of a digital device and maybe more of an analog device. And even with Surface, some of the transitions and animations you see, I'm talking about now the tablet Surface, feel so fluid that almost you get a sense that there's actually a physical thing there. And some of the multi-touch interactions, you get this sort of idea of, wow, it doesn't really feel like a digital thing anymore. It's really an analog thing. And I think that's a very interesting trend, and that's something that I'd like to highlight in some of these videos. The second theme is this notion we're calling society of devices. If you've ever heard Bill Buxton, who's on my team, if you've ever heard him talk, he often refers to this as the society of appliances or society of devices. The notion that we now have, your tablet, your laptop, your phone, your TV, your car, your office computer. Maybe there's a computer in a conference room that you use sometimes. How do these devices work together in a seamless fashion, right? And so that's a very interesting one. What would you do if a tablet actually knew that it was next to your coworker's tablet? How could you make interactions around that? So those are some things. And then finally, I'll show some really fun work that we're doing in this notion of what we're calling mixed reality, or bringing the Surface kind of interaction so that every available physical surface in your world is an interactive surface. And that's kind of an interesting idea. So I'm going to dive right into these videos. And so again, my goal here is to overwhelm you a little bit and sort of show you the breadth of things that we've done. It is still a sort of a slice through the last 10 years of work that I've been involved with. And so some of it's going to look a little old today, but I think you'll find some interesting things in it. So as I mentioned earlier, I worked on the earliest incarnation of Surface, the large tabletop that used computer vision and cameras to do sensing. My background is in computer vision, so I hopped at the chance to build the very first prototype of what we first called the Play Table. It wasn't called Surface. And it was, in fact, marketed as a consumer device, something that you would have in your living room as a coffee table. And let me show you some of the things that we did with that. This is a sort of a very early video that we shot right after we got some of it to work. We had tagged objects, and this is sort of a little bit of a view into that, these little translucent pieces. And this is the days before really multi-touch became sort of a household term. And so we were doing these kinds of things and inventing the future and not really quite realizing it, and doing all sorts of very interesting things with physical objects. For the most part, we really focused on how can we leverage the vision techniques that we had to identify objects placed on the surface. So we had fun inventing silly pinball games, including devices there that actually that had a little bit of a pager motor in it so that it would light up. Using real brushes. Now this is definitely an analog experience, right? You actually can sense the shape of those brushes as they're down on the surface. So you get this feeling that, oh my goodness, this actually behaves like a brush. I know how a brush works. I don't have to select a brush size on a palette somewhere. I actually just use it as a brush. We did some things with photo sorting. The idea of having a physical object that would embody some collection of photos. You'd put it down on your coffee table. There's this carousel idea and manipulation. Of course, all of this looks academic at this point, but back then, this was all brand new. We did some fun things with these transparent pieces. These are actually glass pieces. You built up this puzzle. When you put the glass piece down on, it would light up because it had an invisible code on it. This is probably one of the more fun demos we did, where you actually control a tank. These are these remote control tanks that you can buy. They're controlled via infrared, and the little toy tanks. So one of those tanks is under computer control, and so it runs around. And apologies for the quality of this video, but this one's under the table's control, and then the second one is actually under the joystick control. Actually, in this vignette, this person is dragging a tagged object around, and the tank is driving, trying to follow that. So this blending of the virtual and the real, I think, is a nice supernatural experience, right? So you can do things. We sensed dice, so we did a Trivial Pursuit game where we actually had a real physical dice. We did coins. There was a very quick flash there. We could sense coins, and then all sorts of different things. And so we had a really blast. So that led to the development of Surface. We also looked at different kinds of ways to structure the interaction that's very different. This is what I call surface physics. We did some work to structure the interaction of Surface within a real-time gaming physics engine. So instead of calling set position on an object when you touch it, we simulate the motion of an object by collision detection, collision response, friction forces, all of these kinds of quantities and concepts you have in a real-time physics engine of the sort you find in games. This gives you a really nice, interesting vibe here in interacting with the ball. I can trap that ball with my hand and stop it immediately, or I can just brush the top of it and influence its behavior. Interacting with 3D objects and with a 2D device, as many of you probably have come to know, is a difficult proposition. We tried some various things. The idea that you could manipulate a stack of cards in a 3D environment with a 2D device was something that was kind of interesting and difficult. And of course, when you have a real-time physics engine, you can't help yourself but play with these kinds of cloth simulations and other kinds of interesting, again, analog feeling interactions. Now, a cloth is something that's is a little bit difficult to simulate, and interacting with it is interesting. It's not immediately clear what this is useful for, but it was kind of fun to try, for example, folding a piece of cloth. And right now, I think we can probably get away with just one fold. Doing another fold or some sort of origami is probably beyond what we can do today. So that's surface physics. So one last example here. This is a little bit of a tearing. The interesting thing about this example is that while you were doing it, it's almost like it felt like you were doing it, like you were tearing a piece of fruit roll-up, if you will. And it's had a very sort of almost kinesthetic feel to it. This is how it works, actually. Really quickly, I want to go over some of the image processing. In the bottom right, you see what the surface cameras see, and it pulls out the edges of the input, and then we plop down rigid body objects, these red pencil-like structures, into the physics scene. We use as many of those as we need to approximate the contours, and then we apply forces to match the motion that we observe in the image. So that's a very different way to structure things than what we're used to in multi-touch processing. Just for the fun of it, I decided to spend an afternoon structuring some of the traditional UI widgets using a physics engine. It's kind of silly, but it gives you some interesting behavior. There's a scroll viewer. The first example there was a list box. Here's kind of a knob. Now they're all kind of, they need a lot more tuning than I gave it in my experiments. And here's a kind of a trackball-like thing. And this is all just using constraints in a typical physics engine. If you've ever programmed a physics engine, you're familiar with this concept, where you can constrain objects to lie within a line, for example. Here's a switch. Again, it's a little floaty, something you would definitely need to spend some time on. And then what I do here is, the next bit is rotate the camera so to reveal how some of these objects are structured. So that list box there is, in fact, a big wheel. So it's a very unusual way to think about widgets. It's funny to think back on at Xerox PARC when they started thinking about these kinds of widgets. They took inspiration from real physical devices like radio buttons and sliders and control panels and so this is a very literal interpretation of that. That maybe it's worth revisiting. I'm not sure. So then you see the list box is in fact this giant textured object that is basically constrained to slide within a line and has stops at the front, at the top, and the bottom. Here's a very, very early depth camera demo that really illustrates the whole idea of analog interaction very nicely. Those are virtual cars, and we can project those cars down onto a tabletop. We're using a time-of-flight depth camera. This was in around 2006 we did this work. And as I put down an object in the scene, it behaves appropriately, right? So it takes the jump as you would expect. Now, this is not because it recognizes the jump, the piece of cardboard as a jump. It recognizes the shape. It's reading the shape of it using the depth camera technology, and that's an important point. So it has this nice analog feel. This is the virtual view. Now there's all sorts of bumps and imperfections in the mesh image there. We had to do a lot of smoothing in order to get something that you could drive a tiny car over, such that every little piece of noise didn't act as a giant pothole that you lose your car in. So you can assemble these little tracks and these little funny experiences, the sort of nice constructionist way, right? So you don't have to. The designer only has a limited hand into sort of how this interaction proceeds. Here's sort of a traditional, racing or arcade view. You get a sense of how noisy that depth image is. Now the color here is being taken from the color image. As you know, with Kinect, for example, you get the RGB image and the depth image, and so you can align those and then combine those. One thing that we noticed right away is there's a real temptation to put your hands into the scene. So we started playing around with different ways to interact with the volume. So here I'm detecting this pinching gesture, and there's a really nice technique that we invented that an undergraduate can implement to detect this. I invite you to look at some of my papers. And that's the depth image we get, and you can drop obstacles into the scene and have some fun with that. Also, there's a temptation to put your hands into the scene and interact with the cars, and so we started playing around with that idea. So the idea that you could lift that car and drive over that car. So in this example is something that you had to do sort of delicately. It was something that was very easy to have the car fall through your hand, but the idea was very interesting nonetheless. And here's the virtual view. Now the softness and the blanketing you see off to the side, of course, is because this is not a true 3D sensor. You could call it a 2.5D sensor, really. You can't see around or through objects, and so you get this kind of blanketing effect. It's as if you took a bed sheet and threw it over your desk. This is the kind of shape you would get with a depth camera. That's true today, even with Kinect. So this interaction with these virtual objects is something that using just your hands and thinking about that and all of the computational techniques and representations that are behind those kinds of interactions have occupied me for many years. So this is one approach. This is a very early PrimeSense demo. This is the very camera that's in the Kinect. And so this is one idea of just taking a bunch of spheres and matching the depth image. The depth camera is actually above the display looking down. And then, so then we just move the spheres into position programmatically at every frame of the depth camera. Now the thing that's really nice and, again, very analog about this interaction is that, contrast this to, if I were to track my hand and put a cursor into the scene and then have some sort of grasping maneuver or something, this is very different. This is about simulating the very shape of your hand and having it respond to all the kinds of bumps and curves of your actual arms and hands, and just making use of that. Why not? Because this is the kind of thing that you do in the real life. You understand these things. You make use of these things, just getting out of bed in the morning. Why not try to reflect that in the real world? That goes on to some other work. We're trying to, again, use the depth camera technology in interesting ways. So we have the ability to grasp an object. This is some very early work. I'm not really happy with the way that this works, but just showing you a little bit of some of the progress we've made over the years. This object is being brought up by the hand, not because there's a routine that says, grabbing equals true. This is being lifted because we're simulating the friction forces and the collision forces using the physics simulator. So it has a very different kind of feel. The idea, of course, is to leverage all of this innate ability you have to grasp things. And you can, if you look carefully, you can see that there is all sorts of mayhem going on as far as penetration and all sorts of problems. So it's definitely something that we're still working on. So I'd like to continue in this analog theme. This is a very early demo of a Surface-like device where we had a projector onto a tabletop. This is a short throw projector. And I like to show this particular example because it again, is very analog, makes very little attempt to process the image. And also well, I'll show you. I don't want to reveal too much, but the notion here is that we have two of these units. They're communicating over the network. And so we reflect one person's image onto the other. We rotate it by 180 degrees. We also rotate it actually to correspond with the chessboard so that your chessboard is aligned with my chessboard. The funny thing about this, of course, is that when you're playing chess, and this happened the very first time we actually tried to play a game, is that when your opponent takes your piece or captures your piece, you have to remove it. Now, if you think about it for a minute, that's very different than the way you normally play. And even worse is that when you have to remove that piece, all of a sudden you lose track of whose turn it is. Right? So there's some flaws here, but it's hard to understand unless you actually try it. But you get all these nonverbal kinds of interactions, and of course you don't have to be playing chess. It could be anything. And this is the only real processing we did with this system is to try to match the chessboard. Now this work has really been followed up at Microsoft Research. If you've seen the IllumiShare project, they've done a very nice job of making this into a desk lamp structure and also bringing color into the picture. So we're actually sensing and transmitting color, which is actually non-trivial. So this is drawing. So one of the nice things about this is, again, this analog experience. You know how to use a stylus. Let's leverage that and create this. Now, when I first put this together, I was thinking, wow, it's going to be creepy to have my remote participants' hands come around me and interact in my space. Like somehow this is going to be violating my personal space. You get used to that really quickly. The other funny thing about this interaction, of course, is at the end of this, what do you have? Well, you don't really have a whole drawing. You have exactly half a drawing, right? So maybe what you do is you actually print it. So we continued in this vein of thinking about physical objects and also devices, right? So this is the earliest example of this kind of thing that we did, where you put the phone down, and some of you will recognize this as an old Windows mobile phone, and it pulls the photos over Bluetooth onto the tabletop. And so this is a really nice kind of thing. It's very instantaneous. It's very sort of tangible. You understand it. Somebody who's watching would understand what you're doing. It's not like you're having to wade through a dialog box or some sort of clunky thing. We used infrared DA to do this sort of handshaking so that we could sense what was going on. Of course, you wouldn't use that today. Here's another system that we built, a very large tabletop. We called it, the application was called Pictionary. This was done actually by an intern of ours. And what he looked at was the various ways that people, designers at Microsoft, actually get together and stand at these taller desks. And we also thought about different ways to incorporate a high-resolution camera that's programmatically controlled. So he's takes a drawing and he drags off. It triggers the DSLR above to take a nice high-resolution picture, which is pulled across the USB cable. And then you can snap these kinds of things to an actual real whiteboard, and then draw on them, and then acquire them again, and do this kind of give and take between the virtual and the real. And if you look at the way designers typically operate, especially when they're in the early stages or ideation, they're all about imagery and annotating imagery, pulling things from all different kinds of sources, things that they draw, things that they find on the web, and all kinds of things. So this was a nice way to explore how we can use surface technology to help designers. This is a remote pointing example. This is probably my favorite. It's almost heretical to think about using a keyboard on these kinds of things, but with the Surface cover, keyboards are back. So with this large table, we had the ability to actually just set the. Oh, I'm going to stop that, because what I want to do is I want to say just a bit more about that. The keyboard. So when you put the keyboard down on it, it would recognize it as a keyboard using the Surface Vision technology, and then would connect over Bluetooth to that. So if you started typing, the text would appear right over the keyboard, and you would execute an image search against Bing, and then your results would appear above it. Now, if somebody else walked up to this unit and put the keyboard down, it would also work for them. And in fact, you could go up to the limit of whatever Bluetooth supports or whatever space you had available. So no sort of login or anything like that. So it was a very sort of interesting suggestion of how we can use real traditional devices, which they're very good at, text entry. And we also had a mouse as well that worked with the system. And that's interesting because you put the mouse down, you instantly expect relative pointing. So you could reach all the way across the desk rather than the sort of touch-based direct manipulation. So I already tipped my hand on the next one. I'm going to let myself explain this video, this system, in the next bit. So the thing to look out for here in this next one is the combination of devices. Sorry, there we go. I'm Andy Wilson, and I'd like to show you a research project we're calling HoloFlector. HoloFlector is an augmented reality mirror. What we're seeing here is a very large translucent mirror, and about 3 feet behind that is an LCD panel that's also very large. And I'm standing about 3 feet away from the translucent mirror. That means if we render graphics on the LCD in life size, I can still see those graphics, and they're basically in correspondence with my reflection. So it looks like the graphics are perfectly overlaid onto my reflection. Or not so perfectly. Now, you'll notice here that you see this, this image of myself. We're getting that from the Kinect sensor, which is placed just above the mirror. The Kinect sensor is monitoring what I'm doing. We're also getting the skeletal tracking data. We also notice that there's a blue ball superimposed onto my right hand. That's basically showing me where the system thinks my Windows Phone is right now. So that's an idea we call sensor fusion. And it's something that demonstrates the complementary nature of the sensors on the phone and the Kinect sensors. So let's have a little bit of fun. So here's a holographic video call that we can see through the mirror. So there's just a video of me. We can imagine this could be a live image of someone that I'd be talking to. You'll notice that it will actually switch from one hand to the next, so I can hold this little version of myself. So it's kind of a fun idea of communications in the future. So as another example of what we can do to combine the phone with the holoflector is we have this basically this wooden paddle that we're rendering. And so one nice thing about using the phone is that we get the nice orientation data from the phone, and we're also using the position data from Kinect. And then finally, we can demonstrate interacting, say, with a fluid simulation. The Kinect data is now colliding with the various particles on the display for this kind of interesting experience. We've seen a lot of examples of augmented reality where you're looking at a phone and you're seeing graphics superimposed onto a video feed like a camera. And this is much more about rendering graphics onto the real world or the reflection of the real world. And it's also a study of how we can use the mobile phone in a complementary way with Kinect. Thank you. So the thing I wanted to talk a bit about in that video was the notion of sensor fusion. I talked about it just a little bit. You notice that as the phone gets passed from one hand to the next, the position of that blue sphere changes to follow it. Now, that's not because we're using cameras like Kinect to track the position of the phone. What we're doing is a little more insidious. So what we do is we take the accelerometers on the phone, and so we read those and transmit those over Wi-Fi to the host PC. We compute similar kinds of acceleration numbers off of the Kinect skeletal tracking data for each of the hands. So you get interesting motion signatures as you're moving around doing things, and you can compare the phone's accelerations with the accelerations you observe in the skeletal tracking data. And it's not, you don't have to wait for very long, maybe a half second to a second before you can very nicely get a reliable signal that, hey, the phone must be in this person's left hand because that's precisely, those signatures are in precise agreement. And so that's a very clever kind of thing. We call it sensor fusion. But in general, I think we're going to see a lot more interesting concepts related to having a device that's good at certain things, like in this case, the orientation data, and having a nice touchscreen, and having that integrated with Kinect and other devices. Smart glass, I would say, is one example of that. I think we're going to see a lot more, and I'm very excited to see what develops in that space and to contribute some of the basic algorithms there. So moving on to a very different topic, we did a whole bunch of work around different kinds of crazy form factors. Here's a spherical version of Surface. This is believe it or not, it's commercially available. You can buy these kinds of spherical displays, and there's one at the visitor center downstairs, sort of a front projected version. This is a rear projection. In other words, there's a lens inside that's distributing the image, and we augmented that with a camera and an infrared illuminant to actually get the surface functionality on a sphere. And of course, first question might be, why would you want to do this? And well, we try not to ask really hard questions like that too early in a project. We built it and discovered some of the interesting things that we can do. It's not research if you didn't have all the answers. This gives you some of the idea of some of the technology. We use the graphics hardware to do the distortion on the video so that you can render rectangles and have it appear as if they really are rectangular on the surface. So there's kind of interesting things. So and this also will give you an idea of the sensing. And the sphere is interesting, right? Because you can only see in most half of a sphere, maybe not quite half of a sphere. So there are interesting properties there that you can think about. And it's an interesting, attractive device. I mean, people are naturally drawn to the sort of unusual aspect of it. But we went from that to thinking about different kinds of larger experiences that we could do if we actually took the globe off, right? And so if you take this plastic piece off of the top of the sphere, you eventually get a large projection throughout the room, and I'll show you what I mean by that. Here we're taking the roundtable data. This is that omnidirectional video teleconferencing product we had a while back, and mapping that onto the sphere. So it's kind of like the Palantir in Lord of the Rings, if you will. So this is taking some omnidirectional data from Bing and being able to navigate that just by sort of holding onto it a little bit and moving through the scene. It's kind of a completely different experience than you would have on a flat display. So after you take the the ball off of the stage, you can project everywhere in the scene. So rooms typically aren't dark enough to do that. Projection technology is not bright enough, at least for a single projector. So what we did is, it turns out you can buy these inflatable domes. I bet you didn't know that. And quite reasonable, actually. So they're used in education. So what we did is we lit that up with Worldwide Telescope, which is a Microsoft Research software project that basically takes astronomical data and imagery from all different kinds of sources and presents it in a nice view. Now, this video is a little bit hard to show. I debated about whether or not even including it because it's so dark. But I'd like to hope that you have some sense of what we were doing with the interaction, and also this kind of free space multi-touch almost. He doesn't have to be quite so close to this, close to the device. When he does this, he's actually invoking a speech recognition. This is like push to talk, and so we can say, "Take me to Saturn," and the view will slew over to Saturn smoothly. So this is, again, this has very same pinching gesture I showed you a little while back, and shows you a little bit how how it works. Again, you have this sort of optical distortion that you have to confront, and this one touch is actually just a translation, which in spherical coordinates is really a rotation about the view, and then 2 is a little bit more about movement through a 3D scene. There are many different kinds of interaction models. Again, here's 360-degree video conferencing, where we just again mapped the round table video to the projection surface, and we had that working in real time. And yeah, so you can imagine plopping down one of those round tables in some sort of maybe a rock concert or something like that, and somebody can then experience that in a much more immersive way remotely. And then some of the stuff that we've done with omnidirectional panoramic imagery. This is a topic that we've been studying at Microsoft Research for years. Just plop that in there, and it looks really good. And it's really hard to convey how immersive this experience is in this video, but it really was the kind of thing where if you put somebody in there, it was just like they were completely transported to a different world. And it's very different, I would say, than a planetarium, because when you're actually driving the thing, you get a sense of your own motion through the scene. Here we're taking a scene that was rendered in XNA. Actually, we rewrote part of the default shader that's used in XNA to account for the warp. And if you render a 3D scene and do all the proper warping, you actually feel like you're in a 3D scene. So it's kind of fun. And then we also just playing around with laser pointers and this kind of thing, so you could draw, or if you were actually teaching a class or something like that in the dome, you might want to point at an object, or maybe even bring up a menu or this kind of thing. So this is an infrared laser pointer. You don't actually see the light coming out of an infrared laser pointer. And then we also looked at infrared tape, infrared reflective tape, and the idea of being able to get a signal when you do this, kind of like a click that you might have on a touchpad. And then just playing around with different ideas of having multiple users. This was just a silly pop the bubble kind of game that we played around with. It was multi-user. So that was the dome. By the way, the first version that we built was made out of cardboard, binder clips, and a bucket of latex paint. And so if you're interested in building one of these by yourself, please contact me. I have lots of suggestions on what to not do. If you don't care to buy one of these inflatable ones yourself. But it was the project was hysterical. We really enjoyed it. But it led to something interesting, right? We were starting to think about, well, this is really nice, but of course we don't really want this kind of structure. That's my cohort, Hervé Benko, and so we work on all these projects together. And it's not the first time you saw him, but so this is Lightspace. What we did was take multiple cameras, multiple projectors, strip away the dome, and gain some of the power of having multiple projectors. Now the system is very much more complicated, right? You can expect a lot of cabling and issues and calibration and stitching multiple projectors and multiple cameras together. And here you see the unified view that you get when you stitch 3 views together. This was actually using the depth camera before Kinect. And we have various kinds of interactions that we explored, where we're superimposing graphics on the real world. And there's just a real simple interaction. This part of the video I'm just going to run through. Yeah, there we go. And then we'll go through some of the interactions a little bit more in detail. So the idea really is, what I would love to have happen is, instead of having a kind of chandelier or a projector or something in the center on your ceiling, you install one of these things, which has the sort of capability of doing sensing as well as display. So there's no projector trained on that piece of foam core. That foam core just happens to occupy part of the frustum of one or more of the projectors. Right? So we do the calculations, we figure out where the flat surfaces are in the world, and by the way, we're emulating, whoops, that's loud. So he did this transfer by touching a photo on the one surface and then transferring to the other, right? And that's done almost as if the object was transmitted through his body, right? Of course, that's not how it works, but that's the sort of user model that you might have. Now, manipulating this object here is like we're trying to emulate a physical object. It doesn't know or care about hands. It can be placed onto any sort of surfaces observed by the cameras. And then he can walk over to another display and drop that, say, back on the table, or then touch another and then bring it over there. So it's a very different way of thinking about throwing data around a room. Contrast that to screwing around with VGA cables in the conference room. Here's a 3D menu. So as he raises his hand up and down over the menu marker, he can select various kinds of options. Now the text is oriented so that it's readable for him. And we do that, of course, using the cameras. We just detect the highest point on the blob that is in that volume. See, now you're starting maybe to figure out what's really going on here. We are using the shape information and the connectivity and the mesh data that we get from Kinect. Let me explain that. This is the 3 depth camera views. The depth data we're getting these days with Kinect is a little better than this, and so a lot of the optics and that sort of thing were refined in the productization effort. So we take those three views together and we stitch them together. The white stuff there is basically the static things that we observe when there's no one in the scene. So when you walk into there, you're segmented out as a moving individual or as a user. So you get a random color assigned to you. So when somebody else walks in, maybe the blue, you get blue or something like that. This shows you some of the calculations. The nature of what we're doing with the ball. The mesh is quite noisy, but it's good enough to be able to do some kinds of manipulations. And then this is the view of the menu. So one interesting and fun thing that we did very early was try to emulate the surface behavior. And this is the surface with video cameras, where we essentially construct a small region above the flat surface, the table, so that when you stick your hand in there, you actually create a blob or a sensed object in the scene. We could do that with a wall as well, and then we basically just pass that off to the surface pipeline that we have, the multi-touch pipeline, so we can do this sort of traditional rotation, translation, and scaling maneuvers. We can also calculate a plan view, and so this is all done basically by traditional graphics projection operations. So we're taking an orthographic projection of all the 3D data that we have there to generate that plan view. So when we detect that motion, what we're looking for is an object in both the wall and the table that is connected through another object in the plan view. So when we detect that, we know we know that there's this connectivity that's happening there. So there's no skeletal tracking or anything like this. This was done before that, before the skeletal tracking, but I might argue that this is the right way to do it rather than skeletal tracking. Not sure. So after we did that, we walked into this other project called Mirage Table, where we started thinking about, well, let's do something a little smaller, something that's a little bit more like a desktop. And so what we did was hang a projector above this curved surface. This is basically just a piece of cardboard that's sort of mounted in a particular way that gives a nice curve. And the interesting thing about this, of course, is that you don't detect, when you're sitting in front of it, you don't really detect that it's a curved surface. You don't really detect anything, right? You don't really see anything. There's no edge there to highlight the fact that it's a desk, right? That means that you can put the graphics anywhere in the scene and fool the eye. So we have all of the same kinds of physics-based manipulations that I showed earlier with the spheres and that sort of thing. We're also doing a bit of head tracking. With one Kinect, we're sensing the hand gestures and also the tracked hands and the head tracking. And so as you move around, you get this nice sense of volume in that through parallax. We're also looking at various kinds of distortions on the projection so that it seems as if there's a real object in your hand from that particular point of view. This is a very nice application of projection mapping. Even if part of the object sits on your hand and then part of it falls on the background, from your point of view, you have the correct experience. We played around with different ways to digitize objects. So you plop them down and you invoke a command, and actually you can start accreting these shapes and build a little little structure of columns and whatnot. So here he actually has digitized this little bowling pin, little scale bowling pin, and then each one of these things can then be entered into the physics simulation, and he's going to, well, you can expect what he's going to do, and you can see that one pin is actually still teetering on the edge. So it's kind of fun. You get this kind of interesting kinds of interactions in this tiny space. We also looked at video conferencing. So here is a really nice sense of immersion. When you're sitting in front of this, you really get a sense of that person's right there in front of you. And in fact, because the spaces are joined or aligned or I guess let's just say overlaid one another metrically, that he's even whipping out a tape measure just to prove a point, you get a nice shared workspace. And so there's a very nice system there. So I'm really excited about what we can do with teleconferencing. Here's the evolution. So moving from light space to the Beamatron, which is one of the more recent works that we have. This is saying, let's go from 3 or 4 projectors to 1. And now we're gonna draw on a bunch of different things that I just showed you to create this experience. Again, being able to hold an object in your hand. You saw this before with the car, but now we can drive it anywhere in the room, not just on the tabletop, because that pan-tilt mechanism that we have can actually direct the graphics and the sensing anywhere in the room. If we hit a person, or if we see a person, the skeletal tracking of Kinect detects that more or less automatically, and so we can do some things like follow a user through the room. We also played around with different ways to use the array microphone technology in Kinect, which is excellent. Within an afternoon, we had 3D sound source localization working by using 3 Kinects plugged into one PC, using the Kinect for Windows SDK. And then, if you think about it, that's going to give you 3 planar constraints. So you can calculate the 3D position of the speaker, and then it turns to that person. That's how you get its attention. Any Portal fans out there? Yeah. Hopefully we don't do that. The Beam-A-Buggy is basically the same demo I showed you 20 or 30 minutes ago, and so now we're using the wireless wheel, which is a whole other story. I was participated in the coding for that. We're using the projection mapping so that it appears as if it's a 3D car for real out there in the world, depending upon on your head position. We also have stereo projection as well to make that even more 3D looking. And the physics simulation is running, so we get the sensation that there's actually a real object there. This is kind of an augmented reality experience. I don't normally think of it as augmented reality because it just feels like it's right there, but it really isn't. So augmented reality without looking through a mobile device or wearing glasses or some of the other tricks that AR people do. So this is the stereo view. Of course, you can't see that in this presentation, but she's having a good time there looking at that car in full 3D. Right? We're using Kinect Fusion. This is an interesting project out of Microsoft Research, Cambridge, UK, to build a nice model of the surface geometry in the room. You'll notice she can move that cardboard ramp, and that updates that model in real time. And so that's a really nice thing to look into.
Beamatron.
Here's another demo that we did. Gets attention, and it swivels over to her, and the skeletal tracking starts and homes in on it. And then this is sort of a visualization of the accuracy of the skeletal tracking with respect to the projection and the calibration and all the things that we had to do in order to get this to work. The system is fully 3D. So that if you're an application developer and you want to say, put a graphic on this 3D point, that's easy for the system. It'll calculate the joint angles and all of necessary transformations so that we can specify a point in 3D and move a graphic to there, account for the fact that the surface geometry is not what you would expect, may not even be flat, and then hang it so that it's right side up, or with respect to some sort of normal within the 3D world coordinate volume here. If you've ever seen the ancient Put That There demo, yeah, from MIT back from 1978, this is our little homage.
Next slide.
So who knows? Maybe this will be the way you do a presentation in 2020. So that's the device. This is the. If you were to come to my lab, today, this is the demo I would probably show you. Of course, we'll probably tear it down and do the next thing soon. We only have so much space. Anyway, so that. We've also done a few things. I don't know. Some of you probably saw me walking around with a very strange device on my shoulder at the welcome reception the other night, Monday night. And this is a wearable projector. We have a laser projector and a small Kinect, a short-range version of Kinect that allows us to project graphics onto your hand. And you'll see the device here in a moment. But we're detecting touch and then multi-touch, in fact, just using a whole collection of the things that I've already showed you, plus a few other little hacks that take advantage of the fact that the field of view is always from the first-person perspective if you wear a camera here. There's the device. Of course, we're not really suggesting that someone's going to wear this. Imagine that it's 20 times smaller. Maybe it fits a lapel on your shirt or something like that. This is the kind of test that we would perform to evaluate the performance of the device. We do user study testing at Microsoft Research. We report on things like how accurate is this, does it really work, so that when we publish an academic paper, people have some confidence that what we're doing is actually it works as well as we claim. And so he's actually trying to follow a path. And the next part of the video shows a bunch of examples. Here we just got a notification which he's looking at, and then he can then select that and then draw a volume or a surface on the wall, and then actually look at that. Look at that document. So part of the idea here was to co-opt any surface in your real physical environment and use that in a smart way. So that could be your hand, could be the wall, could also be a pad of paper, right? So there's a part of the code that actually looks for flat surfaces in the depth image as potential projection surfaces, and then we can also do these little more out there experiences, actually using your body as an input device, which is a very interesting idea. Wearable computing is definitely kind of on the rise, I would say, but it's definitely in academia, at least, it's been studied for a while now, at least 20 years, and so this is one kind of take on this idea. So he's drawing a message, and here's another idea of having a palette in your hand that you can select colors with or edit a document, these kinds of things. Now you see the graphics are swimming or rotating a little bit. You really don't want that. Of course, this is a research prototype. This is work done by an intern, Chris Harrison, at Carnegie Mellon University. And the mixture of having a palette or a set of tools in one hand and then having the application run on a secondary surface is a nice one. This is the depth image. This gives you a little bit of an idea of what we're up against as far as the sensing. And here's looking at actually the surface normal of that piece of paper or that pad, and maybe we can denote from the normal whether that object should be public or private. So I believe, I think that's all I have to show for the video. But I'd like to thank a host of collaborators that I've worked with over the years, including Stephen Batish and Hervé Benko, he just goes by Benko, Chris Harrison, Bjorn Hartman, Otmar Hilliges, and Shahram Azadi from the Microsoft Research UK. And I'd also like to, in closing, before we take questions, call out a couple of other Kinect-related talks. On Wednesday, we have a talk at 1:45, Kinect Design Considerations, and then Thursday, Kinect Programming Deep Dive, if you're interested in some of these things. So all of these demos that I've shown you, by the way, they all are written in C#. think about that for a second. Doing image processing in C# is interesting. At first, when I walked into this, I figured, this is never going to happen. I was a Java programmer when I started at Microsoft Research, believe it or not. And I could never get really good performance without going into the native interface and doing all of this sort of stuff in C++. It turns out you can get really good image processing performance in C# if you use pointers. Yeah, so unsafe code is what I use, and so you can get really nice performance. In fact, I've done a couple of benchmarks on some very complex image processing algorithms that I've implemented in C# and in C++. And maybe it's my C++ coding skills, but I found the C# one to be faster by a little bit. And I'm not really sure why. I'm sure somebody in this building could tell me. But I've been very impressed with the performance. We've also been spending a lot of time in GPU code. And so, for example, I can, with the several of the last demos, we're taking the depth data. There it is. Taking the depth image data from the Kinect and then performing transformations on that for the projector and doing all of that on the GPU. This is the kind of thing that when we first sat down to do this, we did all these kinds of transformations in software and changing the vertex buffer and uploading a brand new vertex buffer for every frame. And that basically that can be very very compute intensive. But if you just load it up to load the whole thing up as a texture to the GPU, call it a 16-bit texture, and do all those kinds of transformations, that's tremendous. So there's all this, people have been playing a lot with general purpose computing, and so we've also been doing some things with the Kinect Fusion code base. The Kinect Fusion project, which I alluded to a little bit, also makes extensive use of the GPU to build a voxel space representation of your room as the camera moves around. And so that's when you go out and you buy the most video memory you can possibly get, so that you can build up the biggest voxel space representation. So we can bring down, you can easily use the 2 GB video RAM on today's graphics cards. Anyway, I could go on about the implementation stuff like all afternoon, but I think at this point I'd love to take some questions. Thank you. And if you have a question, please step up to the mic for the benefit of the people at home. Yes. Try again.
Hello?
Yeah, we go.
Right. I'm Xiaobun Zhang from Siemens Research, and I saw a couple of augmented reality devices or prototypes that you did requires the participant or the user to wear certain amount of devices on your body, and I'm just thinking about the prospect of really applying this into real life, and then maybe in the near future. But how much of a level of intrusive or burden of these devices put on the user do you think is appropriate? And based on that, what do you think of the Google Glass project? So
it's a very nice question. It's central to the whole wearable computing concept, and I believe it's all about cost-benefit trade-off, right? I'm happy to wear the glasses on my face because if I didn't, I'd probably hurt myself. So the cost-benefit analysis there is very easy for me. If I'm wearing glasses or some other wearable device, and it's something that has to be charged every night and that sort of thing, it better well be something that is indispensable to my daily life, right? So that's a very high bar. So I guess another way to answer that with respect to all of the work that I just showed you is that we've been moving back and forth along that continuum. We've been mostly shying away from relying on wearable devices and more thinking about putting infrastructure in the environment. So the Beamatron, for example, this device that's in the ceiling, that is a infrastructure heavy kind of approach. That makes sense. Maybe that makes sense in an operating room or a conference room or something like that, where you actually have lots of infrastructure to begin with. So we don't really know what's going to be the right answer. My guess is that we're going to arrive at some solution where we have everything. We have a mixture of things. If I'm in an infrastructure-rich environment like Microsoft, and I work at Microsoft, I walk into a conference room, I have certain kinds of expectations already. There's going to be some kind of large display device there. So there's already some infrastructure there. It just depends on sort of what you do. Does that answer your question? Yeah. It's sort of a non-answer, but. Any more questions?
I have one.
Yeah.
If you have, say, financial resources well south of $1 billion, and like me, I was a former product designer here, but I'm interested in this stuff. But what's a good source of finding people that can do the actual programming? If you have ideas and things that you'd like to implement.
Yeah.
You have suggestions for that?
Yeah. So, yeah, it's interesting. We do think about this a little because as I've been, I do a lot of coding myself still, and the people that I work with at MSR do a lot of the coding. We occasionally rely on contractors and that sort of thing. So as our plans become more and more ambitious, it's unclear that we can withstand that, and so we have been thinking about what kinds of person do we want to be working in this field, and the best answer I can come up with would be game designers. People that have worked on game engines and graphics, and one of my favorite interview questions against that type of person would be, tell me what a quaternion is and why you should care. If you can answer that, then I'm interested. Yeah. So it's more than a 4-tuple. Thank you. So anyway, it's a great question, and it is a very different style of programming. It has nothing to do with web services and these kinds of things, not yet, anyways. And so we are desperate for really smart people. But the nearest one I can find is sort of the people that work on game engines. Thanks for that question. Yep.
So if I want to get started, and I know Microsoft Research had a website and had some of the Connect stuff on there, which is some of the work that you're doing here. But for projection surface, can I go see some of these videos on the web from the research you're doing?
Yeah, well, almost all of the videos I think that I showed you are on my website.
Okay, so go check your website.
Yeah.
Okay.
Yeah, it would be lovely to say, oh, we can just download the code, but
I know.
I do not want to support the stuff that I write. It's not that kind of code. Yeah, sorry. And there are also papers, lots of academic papers, where we go into more depth. We do a lot of publishing at MSR, so I sometimes forget to mention that you can not only can you see the video, but you might be interested to read about some of the details in the papers.
Hi, this is great stuff, great presentation. I noticed it was all visual that you were showing here, and I was wondering if there was other work that you were doing that you didn't describe here that deals with haptics or that deals with audio, music, other senses besides the visual.
Yeah, that's a fine question. So we are looking at haptics. And we have some other folks at MSR. Designated Tan's group, for example, has been dabbling in haptics, and there's some folks that he's been working with at MSR Asia in Beijing, been looking at various haptics. Haptics is really hard right now, right? Especially haptics, especially haptics at a distance, right? So being able to, shoot a haptic experience from across the room onto somebody is, well, there are a couple ways you can imagine doing that, but without hurting them. So, and actually, one of the things they've done is the AirZuka. Somebody's in here's got to know what the AirZuka is, right? There's somebody has a 6-year-old boy at home. So it's a thing that you pull back, and then what it does is it generates this crazy, this ring of laminar flow air that you can, literally, I could probably hit somebody in the back with this thing, back of the room. And so what he's been doing is playing around with the different ways to aim that, to direct that, and at least give some kind of haptic sensation or something like that. But it's very crude. It's not what you really want, and it's not the sort of the Star Trek way. How do you do this in the holodeck? I don't know. maybe the answer is, think much more in advance, and you actually have to, you do it back here through a wire that sits on the back of your skull, and you fool your brain into thinking it's having a particular haptic experience. But that, that is also another research area that we're looking at, brain-computer interfaces. But that's certainly looking very far out. So the audio part, I have. The only thing that we've really done with audio lately is what I showed with the Beamatron, where we did the sound source localization, right? And so, yeah, we haven't really done a whole lot. I did some earlier work that I didn't show today, different ways to combine the speech signal with gesture, so that if I say, turn that on, the system knows what I'm talking about. And furthermore, because I'm pointing at a light or something like that, the speech recognition is extremely simple, right? Because it's only looking for maybe two things over there, right? Given a 3D model. So we have done a little bit of that, not lately. Now, so the other folks have been looking at speech in different ways to model dialogue. In the larger area of HCI, we have a couple of really interesting projects. One of them is the virtual receptionist, which looks at dialogue modeling amongst multiple people speaking and turn taking and that kind of thing, which is all like really fascinating, very nice work. I think that's my little light here is turning red, so I think I'm probably done. If you want to catch me after the session, and I'm happy to answer your questions. Thank you very much.